Hey there, science fans! Are you ready to dive into one of the most fascinating phenomena in our universe? Let's talk about something truly amazing: light. Light is everywhere, and it plays a crucial role in our daily lives. It allows us to see the world around us, from the vibrant colors of a rainbow to the twinkle of distant stars. Imagine a world without the beauty of a rainbow or the guiding light of stars. Light is energy, and it travels in waves, kind of like waves in the ocean, but way, way faster. These waves can travel through the vacuum of space, bringing us sunlight from millions of miles away. Without light, life as we know it wouldn't exist. It's essential for the growth of plants, which form the base of our food chain. Plants need it for photosynthesis, the process by which they convert light energy into chemical energy to grow and thrive. And we need it to see, read, and interact with the world around us. Imagine trying to read a book or use a computer without light. Light also helps us learn about the universe. Through telescopes, we can observe distant galaxies and stars, expanding our understanding of the cosmos. Light is full of surprises. When it passes through a prism, it splits into a spectrum of colors, revealing the hidden beauty within. It acts like both a wave and a particle, a real head-scratcher for scientists. This dual nature of light is one of the most intriguing aspects of physics, but that's what makes studying light so much fun. There's always a new mystery to unravel, a new experiment to conduct. There's always something new to discover. Whether it's understanding how light interacts with different materials or exploring its role in new technologies, the journey is endless. So, get ready to explore the fascinating world of light and reflection with me. Together, we'll uncover the secrets of this incredible force that shapes our world and beyond. Have you ever looked in a mirror and wondered how it works? That's light reflection in action. When light hits a smooth surface, like a mirror, it doesn't just disappear. Nope, it bounces back. This bouncing back of light is what we call reflection. Think of it like a tennis ball hitting a wall. The angle at which the ball hits the wall is the same angle at which it bounces back. Reflection is kind of like that. It's this simple phenomenon that allows us to see our reflections, the beauty of a sunset on a lake, and even use telescopes to peer into the vastness of space. Now, let's get a little more technical with the rules of reflection. Reflection is a fascinating phenomenon that we encounter in our daily lives, often without even realizing it. Don't worry, they're pretty straightforward. Once you understand the basics, you'll see reflection everywhere. There are two main laws of reflection that govern how light behaves when it encounters a surface. First, the law of reflection states that the angle at which the light hits the surface, known as the angle of incidence, is equal to the angle at which it bounces off, called the angle of reflection. This is a fundamental principle that applies to all reflective surfaces. It's like a perfect rebound. Imagine a ball bouncing off a wall. The angle at which it hits the wall is the same as the angle at which it bounces back. Second, this one tells us that the incident ray, incoming light, the reflected ray, outgoing light, and the normal, an imaginary line perpendicular to the surface at the point of incidence, all lie in the same plane. This means that the path of the light is predictable and consistent. Think of it like a flat sheet of paper. Everything happens on that sheet. This helps us visualize how light travels and interacts with surfaces. These laws help us understand how mirrors work, how we see objects, and even how light is used in technologies like lasers and fiber optics. Pretty cool, right? By understanding these principles, we can harness the power of light in various applications, from everyday objects like mirrors to advanced technologies in communication and medicine. Light travels incredibly fast, about 299,792,458 meters per second in a vacuum. This speed is so immense that it's almost beyond human comprehension. Imagine being able to travel from New York to Los Angeles in just a fraction of a second. That's roughly 186,282 miles per second. To put that into perspective, if you could travel at the speed of light, you could circle the Earth 7.5 times in just 1 second. That means light from the sun takes about 8 minutes to reach Earth. This journey covers a distance of approximately 93 million miles. So when you see the sun, you're actually looking at it as it was 8 minutes ago. That's fast enough to circle the Earth over 7 times in just 1 second. This incredible speed is what makes light such a fascinating subject of study in physics and astronomy. We can describe light's speed with a simple equation, c equals lambda mu. This equation is fundamental in understanding the nature of light and its behavior. C represents the speed of light. It's a constant in the universe, meaning it doesn't change regardless of the conditions. Lambda is the wavelength of light, which determines its color. The different colors we see in a rainbow are due to the varying wavelengths of light. And mu, is the frequency of light, which is how many waves pass a point per second. Higher frequency means more waves pass a point in a given time. Different colors of light have different wavelengths and frequencies. For example, blue light has a shorter wavelength and higher frequency compared to red light. Red light has a longer wavelength and lower frequency, which is why it appears at one end of the visible spectrum, while violet light has a shorter wavelength and higher frequency, placing it at the opposite end of the spectrum. But no matter the color, all light travels at the same speed in a vacuum. This uniform speed is a fundamental property of light. It's a universal speed limit. Nothing can travel faster than light in a vacuum, making it the ultimate speed champion in the universe. Now, imagine light has a mind of its own, a slightly lazy one. Light always wants to take the fastest path from point A to point B. This laziness is actually a fundamental principle in physics called Fermat's principle. Fermat's principle states that light will always travel along the path that takes the least time. It might seem counterintuitive, but light doesn't always travel in a straight line. If there are different materials involved, like light passing from air into water, it might bend to find that quickest route. Fermat's principle helps explain why light bends when it goes from one medium to another, like from air to water. This bending of light is called refraction. Light travels slower in water than in air, so to minimize travel time, it bends its path. Think about a lifeguard running towards a person in the water. The lifeguard can run faster on the sand than swim in the water. To reach the person quickly, they'll run in a straight line on the sand and then angle their path once they hit the water. Light does something similar, bending its path to take the fastest route. We use mirrors every day, but have you ever thought about the different types of mirrors and how they use reflection? There are plane mirrors, which are flat and give us a true-sized image. Then there are curved mirrors like concave and convex mirrors. Concave mirrors, like those used in reflecting telescopes, curve inward and can focus light. Convex mirrors, often used as security mirrors in stores, curve outward and give a wider field of view. All these mirrors rely on the laws of reflection to work their magic. Section 8. Numerical fun with light. Let's do a quick calculation. Imagine a beam of light travels from the sun to the earth. The distance between the sun and earth is about 150 million kilometers. How long does it take for the light to reach us? Remember, the speed of light, or c, is 300,000 kilometers per second. We can use the formula time equals distance divided by speed. So time equals 150 million kilometers divided by 300,000 kilometers per second, which equals 500 seconds. That's about 8.33 minutes. So the sunlight we see now left the sun over 8 minutes ago. Pretty amazing, huh? Section 9. Light's bag of tricks, diffraction and refraction. Reflection isn't the only trick up light's sleeve. Light can also bend around corners, a phenomenon called diffraction. It's why we can hear someone talking around a corner even if we can't see them. We've already talked about refraction, where light bends when it changes speed going from one medium to another. This bending is what makes lenses work, allowing us to focus light in eyeglasses, cameras, and telescopes. Section 10. Light in our lives, from vision to technology. Light plays a vital role in our lives. Our eyes detect light, allowing us to see the world around us. We use light for communication, from the blinking lights of traffic signals to the fiber optic cables that carry internet data. Light is also essential for many technologies. Lasers, used in everything from barcode scanners to medical procedures, rely on the properties of light. Solar panels convert light energy into electricity, providing a clean energy source. Light truly is all around us, impacting our lives in countless ways. Section 11. Keep exploring the fascinating world of light. So there you have it, an overview of the amazing world of light and reflection. We've learned how light bounces off surfaces, the laws that govern its behavior, and how it travels at incredible speeds. We've even explored some of light's other tricks, like diffraction and refraction, and how these phenomena are used in everyday technologies. But this is just the beginning. There's so much more to learn about light, from the mysteries of quantum physics to the vast distances it travels across the universe. So keep those curious minds engaged and never stop exploring the fascinating world of light.